नमस्कार, सुस्वागतम, अभिनंदन, केम छो, वणकम, आदाबाज, सत श्री अकाल, खंबागड़ी, वेरी गुड आफ्टरनून। मैं अनिल भारद्वाज आप सभी का पीआरएल के अमृत व्याख्यान में स्वागत करता हूं, अभिनंदन करता हूं। आई अनिल भारद्वाज warmly welcome all of you for the 87th PRL Kamrit Vyakhyaan. This Vyakhyaan is also the 12th Vyakhyaan in the series of PRL Kamrit Vyakhyaan 2.0, which we started on 30th of January 2023, that is beginning of this year. After we completed 75 episodes of series of Vyakhyaan, which we started on 4th of August 2021. PRL, established by Dr. Vikram Sarabhai, the father of Indian Space Program, celebrated its 75 years along with Azadi Ka Amrit Mahotsav, which is the celebration of 75 years of India's independence. Hence, PRL Ka Amrit Vyakhyaan is a celebration of cherishing the history and legacy of PRL in the area of physics and space sciences. Today, that is 29th of December 2023, we have yet another very distinguished Vyakhyaan Karta with us today, Professor Balasubramanian Sundaram of Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore. And he will be delivering the Vyakhyaan on the topic addressing chemical complexities through molecular simulations. We greatly appreciate and thank Professor Sundaram for joining us on the 87th PRL Kamrit Vyakhyaan and to deliver this Vyakhyaan to our audience on the WebEx panel as well as those who have joined us live on the PRL YouTube channel. I would now like to request my colleague, Dr. Balasubramanian, to kindly introduce Professor Sundaram to the audience. Over to you, Dr. Bala.
Thank you, Professor Bharadwaj. It is a pleasure to introduce the speaker. Professor Balasubramanian Sundaram is a physical chemist with a Bachelor of Science in Applied Sciences from Anna University, Chennai, and a Master of Science degree in Physics from University of Pune, and a PhD from the Indian Institute of Science, Bangalore in 1994. Following a postdoctoral stint from 1994 to 1998 at the Department of Chemistry, University of Pennsylvania, Philadelphia, he joined faculty in JNCI Bangalore, where he has been a full professor since 2010. As I said, he is a physical chemist, and he is very well known internationally for his work on the computational modeling of molecular materials and liquids. He is a recipient of the Sanna Jayanti Fellowship and the Shanti Swarup Bhatnagar Award in 2011, and an elected fellow of the Indian Academy of Sciences, Bangalore. He has also been awarded the bronze medals of the Chemical Research Society of India and the Materials Research Society of India. His research interests are carbon dioxide sequestration in porous solids, supramolecular polymers, room temperature ionic liquids, and property prediction of molecular fluids, enzyme structure and dynamics. In addition to this, he likes molecules a lot, and as far as I know, he likes carbonic acid. Maybe I can say carbonic acid is one of his favorite molecules. So with this short introduction, we'll invite our colloquium speaker. Thank you.
Thank you, Professor Bharadwaj, and thank you, Dr. Shivaraman, for the kind words of introduction. I'm going to share my presentation now. I hope it's visible.
Yes, we can see your slide. Yes.
Okay. So good afternoon, everyone, and in particular, thanks to Professor Bharadwaj for inviting me for this wonderful series of colloquia that PRL has been organizing under the ambit of PRL Ka Amrut Vyakhyaan. I've seen some of the lectures I listened to on YouTube, and they're wonderful. I'm so happy to be delivering this lecture. So my talk is titled Addressing Chemical Complexity Through Molecular Simulations. I'm trying to point options. There's a point. So, and I must thank the funding agencies, Department of Science and Technology, National Supercomputing Mission, as for a project, as well as the particular HPC machine called Yukti, supported by NSM at JNCSR, based on which many of these works have been carried out. Since I just talked to my students about PRL, some of them have heard about PRL, and I'm guessing that similar, likewise, people in PRL may not be aware of the Jawaharlal Nehru Center at Bangalore, given that we work on different topics of science. JNC was founded to commemorate the birth centenary of Pandit Jawaharlal Nehru in 1999, and early campus buildings started appearing in the years 94 to 95. First faculty were recruited in 96. I joined myself in a couple of years later, 98, and we've been a deemed university since last 21 years or so. Okay, and so we have our own PhD programs, as well as that's postmasters, as well as integrated PhD programs in physics, chemistry, biology, and as well as in engineering mechanics. We take students from all these disciplines as well as from engineering. And current strength is about 45 faculty with 370 students. We have our own hostels and so on, with journal publications of rate of around 300 plus per year. So that's a short story about Nehru Center. You will, whenever if you land in Bangalore airport, you cannot get into the city without passing us. So we are closer to the airport than anybody else. In today's lecture, I'll be focusing on a particular technique called molecular dynamics. Just to give a general introduction to the technique, this technique was awarded, this technique was recognized through the award of the Nobel Prize in Chemistry in 2013 to three brilliant individuals, Martin Karplus, Michael Levitt, and Aria Warshall, who worked on what we now call as bioinformatics, drug design, and so on. So essentially, in principle, they were working on the structure of proteins, how biomolecules function, enzymatic catalysis, enzymatic reactions, and so on. So the basics of these techniques were developed about 60 years ago. In fact, at JNC, we are organizing a major international conference in February, and marking the 60th anniversary of the very early papers in this using this technique. And in particular, my group has been focusing on molecular liquids, and to illustrate the difficulty in understanding liquids, I'm showing you a picture of the structure of water ice. I have been very careful. I used to, until I met Dr. Balasubramanian and others, I used to call it, I used to understand ice as just water ice, but later I learned, after interacting with lots of atmospheric chemistry people, I learned to qualify it as water ice. So here is a structure of water ice, crystal structure, and there's only one unique structure. So in principle, Bloch's theorem is applicable, and you can obtain, since you have the crystal structure, you can predict all the properties of this crystal by applying quantum mechanics or any higher level theory. Whereas the equivalent approach for a liquid substance, this is also a condensed matter, is not trivial, right? Because it has, unlike the crystal whose entropy is 0 at 0 Kelvin, a single configuration. Here I have configurational entropy, and even for a simple molecule such as water. And if you have a larger molecule than water, then you have something an additional complexity called conformational entropy, where molecules can change shape as well, right? So you have a huge number of configurations and conformations at a particular thermodynamic state point, which makes theory and very intractable, right? So you have phase space variables which are manifold, millionfold, and how do you do this configurational integral, or how do you get the partition function for such a complex system which does not have an intrinsic structure descriptor? Okay, so that's the difficulty, and that's why one takes recourse to modeling, to a bottom-up approach, and trying to model these set of substances using computational tools. And the specific equations of that govern this particular technique are rather simple. These are known to everybody: Newtonian dynamics, written in two first-order differential equations like this, where R and the P are the coordinates and momenta of the degrees of freedom, right? In this case, of all the water molecules, or of the oxygen atoms and the hydrogen atoms constituting the molecule. Now, the time derivative of momentum is the force on the atom. The force on the, what's the force on the atom? That's the negative gradient of the potential that this atom experiences. And this potential comes from all the neighboring molecules that's there in the condensed state. What is the nature of this potential? Nobody knows, right? You can do accurate quantum mechanics and determine this potential. However, then this formalism gets quite intractable for a condensed system having several hundreds of thousands or Avogadro number of degrees of freedom, right? So U is typically approximated using classical forms, but having a quantum chemical basis, and it's usually written in as a polynomial expression or a functional form with parameters. These parameters are usually tuned so that the experimentally known physical properties are reproduced. And this could consist of terms for electrostatic interactions, weak interactions such as hydrogen bonding, van der Waals interactions, and those which involve size of the atom, which primarily comes from the Pauli's exclusion principle. So I'm giving you pictures of different intermolecular interactions that could be built into this U of R, such as, for instance, we assume the immutability of bonds, and we can have a harmonic bond potential, a harmonic angle potential, and something called a torsional potential, which allows molecules to change their shape. We can have interaction terms which capture van der Waals interactions, hydrogen bonding interactions, and of course electrostatics. So these are the specific functional forms that people use, and the sum of all these terms is the total potential energy, and the collection of interactions is what is called a force field. I must tell this particular audience that this field is quite mature. Many of the drug molecules that are prescribed currently for rare diseases and so on are obtained through such an approach. Okay. For instance, initially I mentioned bioinformatics, and so on, drug design and so on. All of them, this is the basis. Okay, so one may think that these parameters A, C are all like hand-waving parameters, but no, there is a history behind them. There's 50, 60 years of history, and so they have this field. The parameters have matured to such an extent that one can have confidence in the fact that one is modeling as realistically as possible the particular substance that one is interested in. So specifically in our group, we use our toolbox contains these are the techniques that we use. We use regular quantum chemical calculations, many of which are I gather are used in your laboratory as well, particularly for single molecules or for clusters of molecules. The vibrational spectra, the photo absorption spectra, and the geometry ground state, as well as excited state calculations can be done using these techniques. One can also do periodic ab initio calculations using tractable quantum mechanics such as quantum density functional theory, but at 0 Kelvin. So suppose this is very popular, for instance, in the solid state physics community, as well as in solid state chemistry community, where you can predict properties of with electronic structure of compounds, particularly of crystals and of hybrid nanoscopic systems quite well. However, when you have a liquid state with configurational entropy, you need to sample configurations at a particular temperature and at a particular pressure at the specific thermodynamic state point. So for which you can use the technique that I described a little while ago called empirical potential molecular dynamics simulations. You can also improvise on them by marrying the best of the both worlds by number 2 and number 3. That is, you can do molecular dynamics on top of density functional theories. That means you have a quantum potential energy surface defined by quantum mechanics, and you evolve the time evolution of the atomic coordinates and of the momenta takes place using Newtonian dynamics. Okay. So that's what is called as ab initio molecular dynamics simulations in the literature, and this is much more expensive than the empirical potential molecular dynamics. And very recently, this particular technique has been made more tractable by several orders of magnitude, in fact, using machine learning. And in today's talk, we will see examples of all of these. If time permits. Just to give you a feel for how we pass time in our lab, right? I'm going to show you some couple of movies. This is of a liquid state electrolyte that one of my students, Srimay Mukherjee, has been working on. So we typically we generate trajectories and watch movies. And look at ion motion in electrolytes, for instance, in this case. And in this case, you have both atomic as well as electronic degrees of freedom, where the electron densities are shown in these shaded surfaces, yellow, orange color surfaces, and the nuclear coordinates are shown here. So this is a technique, the ab initio molecular dynamics technique, which I told you considers electronic degrees of freedom explicitly. Here, in this case, there are electronic degrees of freedom are not present explicitly. They're present implicitly through the empirical force field. Here, they're present explicitly. So this is a lot more challenging to do, computationally challenging. These are several interests in my group. Dr. Sivaraman mentioned some of them earlier, but for today's talk, I'm going to focus on hopefully some things that are of interest to people at PRL. Supercritical carbon dioxide, carbonic acid solutions, ethylene glycol is another small molecule on which we have been working, and I will finish by showing some recent examples of how many of these computational complexity can be made tractable by using machine learning methods. First off, this is a phase diagram of carbon dioxide. And very early on, more than a couple of decades ago, we used to work, I was interested in environmentally benign solvents, solvents that can be used in industry, but typically these solvents are what are called volatile organics, right? So they are very good in terms of solvating organic compounds, and that they are very good chemical reaction media for organic reactions. And people had been and continue to look for alternatives which are not non-volatile, A, B, recyclable, and see where extraction of the product after the reaction proceeds. If you want to extract the products out, how easy is it to extract? Okay, and in that regard, several experimental groups abroad had been working on carbon dioxide in its supercritical form. Okay, I'm showing you a simple phase diagram of carbon dioxide. As you know, of course, at room ambient 1 atmospheric pressure, the solid form of carbon dioxide, which is called dry ice, it sublimes, and you see the solid form goes to the gaseous form directly without an intervening liquid state. You can get the liquid state only at higher pressures. And so this is a triple point. This is the solid gas coexistence line, the liquid gas coexistence line, and the solid liquid coexistence line. The liquid gas coexistence line ending in a critical point. The critical point is very close to at least ambient conditions in terms of temperature, but a little higher pressure are required for the to go supercritical. This region of the phase diagram is what's called the supercritical carbon dioxide. One of the good features of supercritical region of any fluid, not just carbon dioxide, is that it has liquid-like densities, but vapor-like transport. So, for instance, I'm showing you here this is a plane. It's a density pressure plane of the same phase diagram. Here is the pressure temperature plane. Here is the density pressure plane. This is at 310 Kelvin. But however, if you go down to 330 Kelvin, which is supercritical, if you double the density, if you double the pressure going from 100 bar to 200 bar, you double the density. In no other form of the substance will you be able to double the density by doubling the pressure. So that's a good, and you see the densities are comparable here, particularly in this range of pressure, comparable to those of any liquid. So you can have liquid-like densities, which is a good, important thing for solvating solutes, but gas-like transport. So you can have much faster rates of chemical reaction. So we were interested in studying supercritical carbon dioxide, and we did lots of ab initio molecular dynamics simulation. And in particular, this work was done by my second graduate student, Momita Sare, who is a faculty member at the University of Hyderabad now. Right? And so we looked at the intermolecular structure of supercritical carbon dioxide as a function of the density. So this is the carbon-carbon pair correlation function. How close are two carbon dioxide molecules in the supercritical phase at a particular density, right? And the x-axis is in units of angstrom. And if you look at the carbon-oxygen GFR, you find a first peak here around 4 angstrom away. That means the closest oxygen atom of another molecule is about 4 angstrom away from the carbon of the central carbon dioxide. And as you increase the density of this fluid, you find a shoulder appearing predominantly at 3 angstrom, right? And when we dissect what is the contribution of to this shoulder, where is this arising from, we find that at 3 angstrom, you find molecules in the equatorial plane of a central carbon dioxide molecule contributing to this 3 angstrom shoulder, whereas molecules in the north and the south pole of any central molecule in the fluid contributes to the peak at 4 angstrom. Okay, so although we may think that a supercritical fluid phase should be devoid of any intermolecular structure, that's not true. Okay, there is quite a bit of order in this fluid as well, right? Which helps to understand its solvating property. its ability to solvate polar molecule, polar solutes can be enhanced by adding a little bit of ethanol, for instance, which is a polar molecule, right? So, and I'm showing you the summary of our results. Here you have an ethanol molecule, and if you have ethanol in a fluid of supercritical carbon dioxide, where will carbon dioxide molecules be found? That's the question we answered in the bulk fluid. And I'm showing you here a picture which represents the arrangement of carbon dioxide molecule around the ethanol molecule. You find that this is the CH3, CH2, and OH. And you find this is the hydrogen that is pointing towards me of the hydroxyl group. And you find that this oxygen has two lone pairs, and the carbon dioxide carbon atom are present exactly towards the lone pair of the carbon atom. So we found strong evidence for the existence of what is called a Lewis acid interaction between the carbon of the ethanol and the carbon dioxide, so of the oxygen of the ethanol and the carbon of the carbon dioxide. There are two competing interactions in this, in the ethanol and carbon dioxide. One is, of course, what I described, electron donor acceptor or Lewis acid base interaction. The way exactly that I described here is shown in this picture. The lone pair of oxygen interacting with the carbon of the carbon dioxide. You can also have a hydrogen bonding interaction shown here. Our work was published in 2006. Okay, and I was surprised to see in 2017 people from National Radio Astronomy Observatory. People in PRL will be more familiar with these addresses than affiliations than I would ever be, as well as Harvard Center for Astrophysics and School of Engineering and Applied Sciences. And they cited our work, and they say that they found the electron donor acceptor or Lewis acid base complexes are found in a ratio of 4:1 over the hydrogen bonded systems. Okay, and they mention our work as saying the isolated gas phase electron donor acceptor ethanol CO2 dimer is calculated to be lower in energy than the hydrogen bonded configuration by 7.5 kilojoule per mole, reference 14, which is ours, right? And to our knowledge, our no experimental observation of either configuration has been reported. Here, in this particular work, they did microwave spectroscopy to show the existence or rotational spectroscopy, which resulted in the unambiguous identification of the EDA complex. So we were particularly gratified seeing our work being cited more than a decade later. I was having a fanciful idea early on, 15 years ago, trying to see if we theoretically predict the existence of crystalline carbonic acid. Can we find out its crystal structure? And is it possible to use crystalline form of carbonic acid as a method to sequester carbon dioxide from the atmosphere, right? Right. It was okay. So that marked our exploration of carbonic acid. The idea was, look, CO2 is a small molecule, triatomic molecule. H2O is also an abundant molecule, triatomic. So what is the compound form of H2O and CO2, which is carbonic acid, right? So carbonic, and then we started exploring the literature on carbon dioxide, which is in fact, even today, there are very, very few papers on carbonic acid, which also explains the pathetic citations that our paper have been receiving in this area. So carbonic acid has three forms, assuming, so as three forms, the cis-cis, cis trans or the trans trans. People call all cis as the physics community calls this as anti-anti as well. This is the stable geometry, ground state geometry. You can have an intramolecular weak hydrogen bonding interaction between between the hydrogen here and the oxygen there. So that's a ground state, followed by cis trans, which is the first excited state in geometrically, and then the trans trans, right? And as many of you would know, and in fact, I had the pleasure of listening to Dr. Balasubramanian's lecture a couple of weeks ago in Delhi, where he talked about the data from Cassini and the data from his group as well, right? So it's there in interstellar space or in comets and so on, right? So I'm showing flashing and selling ice to Eskimos here, right? I'm flashing his own paper, wonderful work showing the VUV absorption band of carbonic acid in water, carbon dioxide ice, and also followed up by another group's work later in 2021. I think his paper was 2019, right? So very impressive work from PRL in 2019, right? Showing the first existence of carbonic acid ice, right? We had been looking for although the crystal structure was not known, the carbonic acid crystal were known since mid-90s by a group in Innsbruck, Austria, Professor Hage, and followed by later by his research group was taken over by another younger person, Professor Thomas Lorting. And I had the fortune of visiting their lab in Innsbruck, beautiful place, maybe 15 years ago, right? So this we had looked at the vibrational spectra of carbonic acid, trying to see if linear oligomers of carbonic acid could reproduce the experimental infrared and Raman spectrum. One of the things that was known about the carbonic acid crystal, the beta form of the crystal, was that it had a center of inversion. So that from the fact that the Raman active modes were in IR inactive and vice versa. So we proposed a model where the linear oligomers, doubly hydrogen bonded H2CO3 oligomers as constituting the crystal. So we using gas phase or cluster calculations of up to an octamer, we were able to obtain the infrared and Raman spectra. You can see a comparison of the Raman spectra obtained from our calculations, blue curve, and that from experiments at Innsbruck. Quite an impressive comparison, I should say. Right? And this work was done by one of my brilliant students who taught me a lot, Sandeep Reddy, who is at IIT Kharagpur. In case any of you are interested in modeling, accurate modeling of different ices, please consider approaching him. Okay. And then we later wrote a feature article in Chemical Communications on the stability of carbonic acid in water. As you know that although the dry form of carbonic acid is stable, right? It's quite stable. Once you add, its stability decreases once you add 1 or 2 or 3 water molecules, and it rapidly hydrolyzes. So, as I mentioned earlier, the crystalline form of carbonic acid was studied by Professor Mayer and followed by Thomas Lorting at Innsbruck. In an aqueous solution from the beta carbonic acid. Earlier in the 90s, they felt that they had an alpha form of carbonic acid, which was later, recently, it was proven to be incorrect. That assignment was proven to be incorrect, and it's actually a monomethyl ester, right? And not an alpha crystalline form of carbonic acid, right? So this is incorrect assignment. The beta form is correct, right? And they showed that at 10 to the power minus 5 pascals, it is stable below 230 Kelvin, right? And infrared and Raman spectra. So we using extensive density functional theory calculations as well as ab initio molecular dynamics simulations, we proposed several candidate crystal structures to try and reproduce which one of them would reproduce the experimental spectra. These are crystal structures, and in our opinion, this crystal candidate number 5 in the C2 upon C crystal structure was the most apt one, right? In terms of stability, and which gives a good comparison with experimental infrared spectra. So that was our prediction, and we also predicted that we obtained a phase diagram for the stability of the crystal. The way we do these calculations is that we obtain the phonon modes of the crystal, the vibrational spectra of the crystal, and then we use the vibrational partition function for the crystal as well as for the monomer and for the dimer. And for these species, monomer and dimer, they will have rotational contributions as well as translational contributions to the free energy, whereas for the crystal, only the vibrational contribution to the free energy will be there. And then we can calculate these free energies of each of these species as a function of temperature and pressure, and we can see at what conditions these free energy curves would cross each other, and that would give us the regions of thermodynamic stability of each of these forms, and thus we obtain a phase diagram. And we were, lo and behold, and to our great surprise, and I should say that it was probably very fortunate that it happened to match experiment reasonably well. Our predicted crystal structure was stable up to 212 Kelvin at 10 to the power minus 5 Pascal. Experimental value was 230 Kelvin. Okay, this is I still get goosebumps looking at this result. Right. Recently, so this was followed up by several experimental works. Our work also showed that at ambient condition, you can have carbonic acid crystal at very high pressures, and our work has been cited by this paper, which appeared in later on in, I think, 2015 or so in Scientific Reports, where they found solid form of carbonic acid at high pressures and high temperatures. Right. Of course, there is no crystal structure here. Very recently, that is in 2023, a crystal structure of per-deuterated form of carbonic acid has been reported by a German group, and I think this has to be a movie. Does this work? Yeah, it works, right? So it's in the P21 upon C, and it was determined, of course, since it is deuterated, you could use neutron diffraction, and that's how they got the crystal structure, right? And I'm thinking there's an opportunity that since you have the VUV spectrum of the crystal, so but there's been no calculation of the VUV spectrum of this published crystal structure. So this is something that should catch your interest. I'll check my time. I think I have 15 minutes to 50 minutes. Please let me know, Dr. Shivaraman, when I should stop. So I want to spend a little time on, so that's the early story on carbon dioxide and carbonic acid. We have been interested in small molecules, and in particular, I want to bring to your attention another small molecule on which a good amount of rotational spectroscopy as well as vibrational spectroscopy has interest is there. This is on ethylene glycol. It's a small molecule. So you have a CH2 group here, another CH2 group here, and OH here, another OH here. So it's a what's called a diol dialcohol, two alcohol groups are there. It can exist in two dominant conformation. One is denoted using the conformational state of the central carbon-carbon dihedral. That's the only dihedral of importance. There's also another dihedral, terminal dihedral, that's of lesser importance. So if you look at the central carbon-carbon dihedral, since it's a single bond, it can adopt, it is reasonably flexible. So this is in the trans conformation. So you see that the two oxygens are farther away from each other. And in the gauche conformation, they are closer to each other. And this is the ground state. This is the geometric ground state due to something known as the gauche effect. I don't want to get into the details of the gauche effect. What is interesting is that this is the gauche state is the ground state in the gas phase. That means in the gas phase or at low pressures, this is the form of ethylene glycol that is found. In the crystalline phase as well, ethylene glycol exists in the gauche conformation. Whereas in the liquid phase, its conformation is unknown, right? Okay, its conformation is unknown. There are several conformations that are possible for ethylene glycol. In the previous slide, I showed you two of these conformations, but depending on the terminal dihedral also, you can have several conformations, right? And the very early work on the liquid phase of ethylene glycol was determined in India from Bangalore, Krishnan and Krishnan, one of whom was Professor C.V. Raman's student. This was the first paper to report the presence of trans conformers in liquid ethylene glycol, right? And how did they do that? They looked at the Raman and the IR spectra of liquid ethylene glycol, and they found two strong polarized Raman lines of the liquid. They did not have corresponding IR absorption bands at all. So that suggests that a center of inversion of the molecule in the liquid state. And strangely, these Raman lines, which are existing in the liquid state, they disappear on solidification. Okay, they have been attributed to the trans conformation of the glycol molecule. Very interesting work. However, the percentage of molecules that is present of trans molecules in the liquid state was unknown. Later, NMR, people with NMR, they suggested that the trans percentage is 14% and the gauche is 86%. Very recently, about 6-7 years ago, people in IIC, Professor Vasudevan's group, they relooked at the results of Krishnan and Krishnan, and they find here that the blue spectrum is the Raman and the black is the IR absorption, and they find that while these orange colored bands, modes are present both in Raman as well as in IR, the green colored bands are only Raman active, but IR, there is no corresponding IR absorption, right? So that tells you that these bands are arising from molecules with trans conformation, which has a center of inversion. They also did ab initio molecular dynamic simulations using a code called CPMD, and they found that the population of trans molecules is around 20% or so. But however, there was no empirical force field. I was telling you early on that having an empirical force field is useful because you can have very large system sizes which are not amenable for ab initio molecular dynamic simulations, right? So it's important that one develops a force field for liquid ethylene glycol, and so that is the effort that we set out to do. Right, I will skip these slides, and that's the effort that my student Anjali Gaur, who is going to submitting a thesis in a couple of months, that she embarked on, and she developed a force field for the accurate modeling of liquid ethylene glycol, which will have this conformational entropy built into the force field, and to ensure that we are on the right path, we too did the ab initio molecular dynamics simulations, and we too confirmed the results of Vasudevan from Indian Institute of Science, and determining the percentage of trans conformer ethylene glycol molecules in the trans conformation to be about 20% or so at ambient conditions. So how do we do this? We essentially tinker with the torsional potential of the central dihedral angle based on accurate quantum chemical calculations, and then refine the non-bonded interactions to be able to reproduce the, what are called the intermolecular pair correlation functions. With these, with the refined force field, we are able to reproduce almost all the properties of bulk liquid ethylene glycol, such as for density as a function of temperature. The diffusion coefficient is an important quantity, self-diffusion coefficient. The blue color circles are experiments, and the other colors are from our force fields, as well as an extremely challenging quantity to calculate is the shear viscosity. That too, we nail it, right? And as well as surface tension. So all bulk properties of liquid ethylene glycol are reproduced well with our force field. And with this new force field, we can look at ethylene glycol properties when it is mixed with other liquids, such as, for instance, water. Water and ethylene glycol are fully miscible at all concentrations. And so what happens to the population of trans molecules as we add more and more of water into ethylene glycol? So that's the question we addressed in this work. And we are once again, we are able to reproduce all the properties of the binary solution as well. And what we find is, interesting thing is that x-axis here is the mole fraction of ethylene glycol in a water solution, right? So xEg being 1 means it's pure ethylene glycol. xEg 0 means it's pure water. And in the y-axis, I'm plotting the number of percentage of molecules of ethylene glycol in the trans conformation. As we increase the amount of water, the trans population decreases from 21% in neat liquid ethylene glycol to about 12% in very low concentration of ethylene glycol in water, right? Why does this happen? This happens because if you look at the dielectric constant of this compound, that is pure ethylene glycol, it's around 40 or so. And as we all know, the dielectric constant of water, liquid water, is 78. So as you go from the left to the right, you are moving from a less polar medium to a more polar medium. The trans conformer has very low dipole moment because, as I told you, the oxygens are on either opposite ends of the molecule, which means the dipole moment of the molecule will be very low, either 0 or close to 0, right? Whereas in this, when you have only a fewer trans molecules are in the gauche conformation, which are having a very large dipole moment of close to 4 dBi or so, 3.5 to 4 dBi, right? So as the solvent, as the solution becomes more and more polar, the shape of the molecule changes from a trans conformation to a gauche conformation. Molecules which are already in the gauche conformation, that is the 79% of molecules, they continue to be in gauche. But those molecules which are in trans, they change the conformation to a gauche. So that's a beautiful result that we saw as a function of water. And another important work that we got was on the liquid vapor interface, which is, I'm guessing, should be of interest to people looking at atmosphere clusters and so on, right? So I told you that in the bulk liquid, you have 21% of molecules in the trans conformation. So here I'm looking at the liquid vapor interface, and this region of the graph, the molecule, the compound is in liquid form, in this region and in this region, the compound is in vapor form, and I track the molecule shape as a function going from the vapor phase to the liquid phase. So as you notice, in the liquid phase, you have 21% trans, and in the vapor phase, you have almost 0% trans. At the interface, you have a more gauche conformation, right, which should affect all the rotational spectra as well as the vibrational spectra, details of vibrational spectra of the molecules at the interface. So this is another interesting result, that is the enrichment of the interface by molecules of gauche conformation of the neat liquid. In the last 4.5 minutes or so, I want to spend a little time on recent developments which have made possible the ability to do molecular dynamic simulations of condensed phases. When I say condensed phases, of several hundreds to thousands to tens of thousands of degrees of freedom at a particular thermodynamic state point at density functional theory accuracy, or what is called as ab initio accuracy, right? Which is less than 1 kilocalorie per mole. And this work was done, spearheaded by my senior student who submitted his thesis last month, Nikki Lavula, and with my postdoc advisor, Professor Michael Klein as well. This appeared in Journal of Physical Chemistry Letters a few months ago. So the problem that we looked at, I'll get to the problem directly due to lack of time. We are looking at, consider pure water, neat water, right? It has a viscosity of about 1 centipoise. And the diffusion coefficient of water molecules is 2.25 into 10 to the power minus 5 centimeters square per second in neat water at ambient condition. If you add sodium chloride in water, and if you track the diffusion coefficient of water, and if you scale it with its value in pure water, the result will start from a value of 1. And in the x-axis, I'm plotting the concentration of the salt, that is the concentration of sodium chloride. The water diffusion coefficient decreases with increasing amount of sodium chloride. However, if you add another equivalent alkali halide salt, cesium iodide, notice that both the cation here as well as the anion, that is iodide, are larger than the species, than the ions in sodium chloride. You find an opposite strange behavior. You find that water is able to diffuse faster in the salt loaded solution than in pure water. It's strange. This is the experimental data. Okay, this is difficult to believe, so I'm showing you the experimental data. It's the original experiments are 100-year-old. See here, Jones and Dole, 1929. Viscosity as a function of the molality of the added salt. Viscosity of the sodium chloride loaded solution increases, whereas that of cesium iodide solution decreases initially up to 2 molar cesium chloride, and later it increases, right? So what is this strange behavior due to? Can we model this strange behavior? Unfortunately, the empirical potential molecular dynamics simulations, as I told you earlier, as I described earlier, we are able to capture this effect rather well. However, they were not able to capture the decrease in the shear viscosity of cesium chloride loaded water, right? This required quantum nature of quantum interactions, right? And I will skip this slide due to we cannot do full-blown ab initio molecular dynamic simulations and calculate shear viscosity. It's almost impossible even with current day HPC resources if you want to really get the quantitative values, right? So what we do is we take configurations from condensed phase, either from ab initio molecular dynamic simulations of a smaller system size, or from a classical molecular or empirical potential molecular dynamics. We then give these configurations to obtain static energies at density functional theory level. Okay, and right, and with that we were able to, and so this is done using a framework called the DeepMD kit. So what we have is two networks. One is an embedding network for which embeds the configurations, which learns the configurations, and we map it to the energies as well. Not just the energies, we learn forces and something called the pressure, a contribution from the intermolecular interactions to the pressure. And this is what we call as the deep potential. So assume that this is more like a polynomial function with lots and lots of parameters. Okay, this is largely hidden to us. The potential is in terms of the weights that are associated with each of these nodes in this neural network. So with this, we can obtain accurate energies of the corresponding to about 0.7 millielectron volt per atom, with an accuracy of on forces of about 20 millielectron volt per atom, when we say this is with respect to what the quantum density functional theory. With this approach, we are able to do very large system sizes, bulk phenomena. We are able to calculate shear viscosities, and I must tell you that we are able to reproduce experiments. The dashed line are the experimental data, and the blue circle here are the shear viscosity for sodium chloride, which is increasing with increasing salt concentration, and for cesium iodide, it is decreasing with increasing concentration of salt. So this required the explicit information obtained from quantum intermolecular interactions, and specifically the reason for the faster diffusion of water in the cesium iodide loaded configuration we analyzed as due to the unstructured coordination shell around cesium ions of the water molecules around cesium ions as captured through this incremental pair correlation functions, whereas water molecules around a sodium ion are more structured. You have a structured first coordination shell and an identifiable second coordination shell around sodium, which is not present in the case of cesium, right? So this is contributed to the facile mobility of water molecules from around 3 angstrom to 5 angstrom. They easily move through, whereas in the case of sodium, they go through a barrier. They go through a low probability region, which would correspond to a barrier in the free energy. So with that, let me stop and show you this particular slide. In case anybody in PRL is interested in modeling condensed matter at ab initio accuracy. When I say condensed matter, I am talking about the first condensed matter, the phase that is first condensed from the vapor phase, which is the liquid phase at the bulk level. Then one can take this approach of using machine learned potentials, and one can model them at DFT accuracy. And I hope I have shown you, this is my summary slide, that hierarchy of computational methods and hierarchy in terms of accuracy, in terms of intermolecular interactions, as well as spatial and temporal dimensions. All of these so that we can realistically model condensed matter. With that, let me thank you for your attention, and I thank PRL once again for inviting me to give this colloquium. Thank you. Shall I stop sharing the screen?
Yeah, you can.
Okay. Define stop sharing.
Thank you, Professor Balasubramanian. Now we are over to questions. I'll pass it on to our colleague, Dr. Rajesh Kushwaha, to conduct the question and answer session. Over to you, Rajesh. Your mic is muted. Your mic is still muted,
We
Rajesh.
can't hear you.
Exactly.
We cannot hear you.
Rajesh, your mic is muted.
Dr. Kushwaha, please unmute yourself.
Unmute.
There.
Acha. Oh, he's
He's
unable to unmute. He just told me. Let's
DST.
just find out. Maybe the moderator can unmute.
Exactly. और आप सडनली क्यों बोल रहे जब कोई आ रहा है? उसे एक पॉलिसी बनाओ ना. जब पॉलिसी बनेगी उसके बाद इम्प्लीमेंट. पहले उस पर डिबेट करो.
Rajesh he just conveyed to me that he's unable to unmute. Maybe request the
I think
moderator.
there is some
to-
issue.
This
I
will
think.
director that you have been
Yeah.
put like this. We correct. You have to tell him.
Bush, can you?
Bala, you can take over.
Okay. Okay. I will take over the questions then. Okay. I think Professor Bharadwaj has a question. So go to you, Professor Bharadwaj.
Okay, thank you, Bala, and thanks, Professor Bala Sundaram, for a very exciting talk talking about molecules and their properties. I was really intrigued by your supercritical carbon dioxide CO2, which you're talking about in the beginning. And you talked about the critical point for this CO2, which comes somewhere around 30 degrees centigrade and some 70 bar kind of things.
Yes.
So I was a little curious to know what would happen if your temperature increases further.
Those are different issues.
Something like.
Why are you making arbitrariness?
Just a second. There is an, I think, Professor Varun Shri, can you please mute your mic? Hello, Professor Varun.
Single logic behind.
Hello.
This toggling actually looks like.
Yeah. Professor Varun, can you please
make a comment?
Mute your mic.
You have to take an action, make it an OM for minutes of the meeting. तो करो.
Hello.
सबसे मुझे बुरा लगा. I'm head of the computer committee.
I think somebody has to call him on phone or tell him.
Okay. Yeah. So
yes,
I was trying to ask you this question about
temperature.
What would happen if the temperature goes still further, from 30 degrees centigrade to something like 100 degrees or few hundreds of degrees, and the pressure also increases somewhere like 100 bar kind of thing.
Yes. Yeah. So yeah, it will still be in the supercritical fluid phase.
Mm-hmm.
Okay. But one of the advantages, I forgot to mention this, is that unlike water, whose critical point is much higher, right? 573, if I remember right? Carbon dioxide's TC, critical temperature, is close to ambient, and that makes it attractive in terms of you don't have to spend so much energy to heat the substance. But my guess is CO2 would continue to be in the supercritical fluid phase. To break the bonds, you would require much higher temperatures, right? Yeah, of course. Yes, that's right. Yes.
I see. Okay. You know why I was asking this question was, if we go to a planet like Venus,
Hmm.
the pressures are somewhere around 100 bar on the
Okay.
surface. It
Yes.
is dominated by carbon dioxide. So Venus
I see.
atmosphere is dominated by carbon dioxide,
Okay.
but the surface temperature is somewhere around 800 Kelvin.
Oh, I see.
So you have a 100 bar pressure, 800 Kelvin temperatures. So
Hmm.
what kind of CO2 would you be, looking
Huh.
for from
Yeah.
your own understanding of
Yeah.
this kind of critical points?
Yeah. So temperature you said is 800 C. Yeah.
800 Kelvin. So something
800
like
Kelvin.
400 degree, you can say.
Yeah. Yeah. So that is still it is still not too probably too high to break the carbon oxygen bond. Probably that would be my guess. It would certainly be much longer. The bond length. And so it will still be in the and you said the pressures are also high, right?
Yes, it is 100 bar.
Fascinating piece of knowledge I'm gaining. I had no idea.
So I wanted to excite you to look at this kind of
Absolutely.
situation which is there in the solar system.
Please bring me back to the ground state so that I can answer.
Okay, thank you.
Thank you.
Over to you,
Wonderful.
Bala.
Wonderful.
Thank you. We are open for questions from those who have joined over us over the WebEx platform. Okay, before we receive the other questions, I have one question, Sir
Yes.
Balasubramanian.
Yes.
You have talked about the ethylene glycol water interaction.
Yes, yes.
So the question is it a common diol water interaction or it is only specific to ethylene glycol and water?
Okay. So if in this specific case, I mean, the only dominant interaction is hydrogen bonding. Ethylene glycol also has a small amphiphilic character because of the CH2 groups, two CH2 groups, right? So that makes it, for instance, enrich the solution air interface. So if you had a solution of aqueous ethylene glycol, and if you looked at its interface with air, then ethylene glycol will be enriching the interface.
Okay.
This paper appeared in Langueur yesterday of ours. I didn't talk about that. Okay.
Oh, congratulations.
Will this be applicable to other diols? Right. The dominant interaction will be hydrogen bonding. So that way they will be common.
So it does not matter even if you have another CH2 group in the middle, like the propanediol. So that does not affect, right?
That won't affect. In fact, if you have a center of inversion, but however, its conformational landscape is richer.
Okay.
Once you have an additional carbon.
Okay.
So that introduces more complexity in mapping out the energy landscape.
Just out of curiosity, what if we replace the central carbon rings with the carbon or the aliphatic rings with the aromatic with the benzene? So, for example, the resorcinol. So we have the diol on either end. OH. There is a benzene at the center.
But the problem with aromatics is that you lose conformational flexibility.
Yes, but the same effect will be remaining.
No. I mean, interfacial enrichment will be there, but however, conformational richness is lost.
Okay.
Yeah.
Okay, but the diol effect will still hold because of these two laws. Okay.
Yeah. May I just one moment, sir. Professor Bharadwaj's thing, I just was mulling over it. The carbon dioxide will surely be in much higher vibrational excited states. So in our work, we are most of the time it was in the vibrational ground state, right? At the Venus temperatures and pressures that you mentioned, it will surely be in much higher vibrational excited states. Will be accessible.
Okay.
Yeah, Bala. I rejoined and now it's I can unmute.
Yes.
Sorry for inconvenience. It was some problem at my side. Yeah, so I can take over. I mean, yeah. So if any question from WebEx, please raise your hand. Meantime, I can ask one question.
Yes.
Sir, your talk was very informative and I was super excited to know that you are handling such a complex molecule, which has so many conformal equilibria. And I was just thinking that at a given temperature, each molecule has different kind of conformal. And once you are going from one phase to other, for
Yes.
example, gas phase to liquid,
Yes.
then how this ratio change?
Oh.
Any comment on this?
Yes. So how this ratio changes? So I was actually showing you the liquid vapor interface of neat ethylene glycol, and you found
Yeah.
this is using an empirical potential, right?
Mhm.
So in the gas phase, you had a 0% trans, and
Yes.
in the liquid phase, you had 21% trans. Why does
Yes.
this happen? Okay, the reason is simple. You're going from the gas phase. Of course, the geometry prefers the Gauss conformation, right?
Mhm.
And you're going to a little more dielectric constant of 40, right? And so there is some amount of trans. More importantly, I would say that very importantly, you have conformational entropy contribution. The liquid
Yes.
state, yeah, is always looking. Liquid state has this entropy, right? Okay.
Yes. Yeah.
And the different channels by which entropy can be increased will always be explored. Okay.
Nice.
And so that, in my opinion, conformational entropy is one of the main reasons why in the liquid state you have this higher trans percentage. Okay.
Okay. Just slightly more things. Yeah. Bala, any question?
Yeah, I have a question.
Yeah, go ahead.
So, sorry, please correct me if I'm wrong. I think in your talk you mentioned the first condensed state is liquid.
Yes.
From the gas, but in case if you take the ultra high vacuum condition,
yes,
the first condensed state itself is a solid when you pass the gas.
Oh, yeah, okay.
So,
okay.
So the question is, in this case, what do you think if when the molecules are condensing, say at 100 Kelvin or at 10 Kelvin?
Yes.
What do you think will be the differences that we could see?
If any molecule?
Like say for example, water we can take.
Okay. So
water when you freeze at 150 Kelvin in UHV, it is turning amorphous, crystalline.
Yes.
Directly you will get a crystalline phase. But
Yes.
the same thing when we condense at 100
yes.
or 10 Kelvin, it is amorphous.
Yes.
Yeah. So can you please comment on that part?
Yeah. So yes, thanks for your correction. First of all, I am biased by ambient condition. I was biased. I should not have been. Okay.
Oh, no, fine.
Yeah. So interesting questions. I mean, as far as the crystal nature of the crystal structure is concerned, it should be that particular phase which is most stable at those conditions, right? Water ice has when I used to study, it used to have 13 phases, but now probably has more phases, probably 15 or 16.
Mm-hmm.
Okay, so I'm not sure which particular phase is stable at those conditions that you mentioned. Yeah.
No, but when we condense at very low temperature, they are only amorphous.
Oh, I see. Okay.
They don't have enough energy to make the crystalline phase.
Okay.
When they condense from the gas to the solid at that
probably you need the energy for a nucleus to form, and for the crystal nucleus to form and get stabilized. Else you end up in the amorphous phase. Probably, I'm not sure. Okay, but this is something in our group we have not been looking at this, but I'm guessing several groups must be looking at this nucleation of different forms of crystal at different thermodynamic conditions.
Okay, because water is still an interesting molecule to
absolutely
at very different conditions.
Absolutely.
Okay, thank you.
Thank you.
Thank you.
There is one question from YouTube. I have just copy and paste in chat box. So the question is, when interatomic potential is obtained by fitting parameters, does one get any intuitive understanding about the existing interaction which may extrapolate it to obtain similar molecules?
Answer is yes. In the case of empirical potential, thanks for asking this question. In the case of empirical potentials, they are always attempted so as to be transferable. The question, the word that people use in the literature, technical word, is something called transferability. Can you take the carbon from ethylene glycol and use it as a carbon in, let's say, butane or decane or something like that? Answer is yes. Okay, so transferability is sought after. In the case of machine learned potential, so for transferability, you obviously have to have intuitive understanding of the intermolecular interaction and being able to represent it in terms of classical forms. In the case of machine learned potentials, it is not transparently available, but somewhere it is hidden somewhere, okay, in those neural network weights and so on, and in the framework of the neural network, right? Currently, there is one is people are researchers are not interested in actual physical understanding of the machine learned potential per se, but more in its ability to represent the substance of interest in an accurate fashion, and what it can deliver, what new insights one can what new knowledge one can gain with this. So that's where the approach is. The approach has been less on the understanding of why this machine learning potential, how does it, what physics is embedded in it, right? But we should probably be getting there in some time. These are very early days. Machine learning potentials, although the very first paper was in 2007 with Baylor and Perinello, but it took off literally only over the last 5-6 years ago, right? Okay, so we're still in the early stages.
Yeah, thank you. Thank you for this reply. I hope my audience at YouTube got benefited. I do not see much question at YouTube and no hand raise at WebEx. So now we move to the next session, and Manas will take over. Yeah, over to you, Manas.
Vinit.
Oh, hello.
Yeah, Vinit.
Yeah, am I audible?
Yes. So,
Okay.
Vinit, you can go ahead with the vote of thanks.
Okay. Yeah, thank you very much, Professor Sahu and Dr. Rajesh Kushwaha. So that brings us to the conclusion of the 87th episode of PRL ka Amrut Vyakhyaan. And for the foremost, we would like to thank Professor Balasubramanian Sundaram for accepting our invitation and giving an excellent talk on the topic of addressing chemical complexity through molecular simulations in today's event. We are also thankful to Professor Sundaram for answering the audience's questions. Next, I would like to take this opportunity to thank our audiences on both our platforms, the YouTube and the WebEx platforms. Next, I express my sincere thanks to PRL Director, Professor Anil Bhardwaj, Dean PRL, Professor D. Pallam Raju, and Chair of the PRL ka Amrut Vyakhyaan Committee, Professor Nandita Srivastava, for all their support in organizing this episode and all the other episodes of PRL ka Amrut Vyakhyaan successfully. I also thank my colleagues in Vyakhyaan Organizing Committee for successfully conducting today's episode of the PRL ka Amrut Vyakhyaan series. Kindly visit our website and other media platforms to know more about upcoming events being held at PRL, especially this event, PRL ka Amrut Vyakhyaan. And with these words, I propose for the closure of today's episode of PRL ka Amrut Vyakhyaan. See you next time. Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you,
Thank you, Professor Bharadwaj. Thank you.